In this module, we shall discuss about interval estimation. An interval estimate is defined by two numbers between which a population parameter is said to lie. For example, x lies between a and b is an interval estimate of the population mean mu. It indicates that the population mean is greater than a but less than b. The interval estimate is centered at the point estimate of the parameter value. The confidence level is the probability that the true value of the parameter lies within the confidence interval, where the sample statistic is a random variable. We can have two-sided confidence intervals and one-sided confidence intervals. Once the single sample has been selected and used to arrive at the interval, it is no longer a probability statement, as the calculated sample statistic is a constant for that sample. The confidence level is a measure of the reliability of the estimate, and the width of the interval is a measure of the precision of the estimate. Higher the confidence level, greater is the reliability. Smaller the width, greater is the precision. As the confidence level is increased, the width of the interval also increases. Thus, reliability and precision are inversely related for given sample size. Both reliability and precision can be increased simultaneously only by increasing the sample size. However, this is only possible in the case of two-sided confidence intervals and if critical values of the standard normal distribution are being used. After studying this module, you will be able to know about confidence interval for population proportion, know about confidence interval for population variance. First, we shall discuss confidence interval for population proportion. Sometimes we can assume that the population from which the sample has been collected is a binomial population. That is to say that the problems involving percentages or proportions of the population having a particular trait can be based on the assumption that the population is binomial. If the sample size n is large, the binomial distribution can be approximated by a normal distribution. Hence, the calculation of population proportions or percentage from a sample can be done using the standardized z variable. For example, a random sample of n is equal to 50 persons' monthly expenditure on breakfast cereal food is taken, and let the relative frequency of persons who incur expenditure on breakfast cereal within rupees 1000 to 2000 calculated be 0.20 or 20%. Thus, we treat the percentage of people who incur expenditure on breakfast cereal within the rupees 1000 2000 as a success and all other classes of expenditure as failure. The problem at hand is to determine how close the sample estimate of 20% is true population proportion of persons who incur monthly expenditure on breakfast cereal within the 1000 2000 range. Thus, confidence interval estimation for population proportion involves determining the accuracy of relative frequency of x by n as an estimator of p, where x is the number of successes and n are the number of trials. Moving on to the estimation of population proportions, let us take a random sample of size n and let x be a binomial random variable. That is, x is the number of successes in the sample, where success identifies an individual or object that has a specified property. For example, X can be number of defectives in a shipment of the transistor, the percentage of school holder with IQ over 115, or the death rate of a disease. Then, as we already know about binomial distribution random variable X, Ex is equal to np the whole over sigma by x, which is equal to under root np into 1 minus p, where n is the total number of trials and p is the probability of success. Hence, we are sampling from a binomial population and the parameter of interest to be estimated is p if n is large, that is np is greater than 10 and n into 1 minus p is greater than 10. The binomial distribution population can be approximated by a normal distribution. Hence, standardizing the x variable by subtracting ex from x and dividing by ox, we get the following z variable. Z is equal to x minus np, the whole over under root of np into 1 minus p. The z random variable has approximately standard normal distribution, and hence the standard normal distribution tables can be used to calculate the interval values. Hence, p bracket open minus z divided by alpha divided by 2, which is less than z, and whereas z divided by alpha divided by 2 is greater than z, which is equal to 1 minus alpha, which is equal to p bracket open minus z divided by alpha by 2, which is less than x minus np divided by under root np into 1 minus p, which is less than z divided by alpha by 2, which is equal to 1 minus alpha. The formula requires that P, or the population proportion, to be known. However, the problem itself involves the calculation of P, or the population proportion. Hence, instead of using the unknown P, we use the sample proportion as an estimator for P. Hence, the approximate 100 into 1 minus x percent confidence interval for P is the following: P hat plus minus Z divided by alpha by 2 into under root P hat Q hat divided by N, where P hat is equal to X by N and Q hat is equal to 1 minus P hat, which is equal to 1 minus X by N, which is the equation 1. Example 1. Of the 400 persons who were given flu vaccine, 136 experienced some form of discomfort. Construct a 95% confidence interval for the true population proportion of persons who have experienced some discomfort from the vaccine. Here, P hat is equal to 136 divided by 400, which is equal to 0.34, and Z 0.025 is equal to 1.96. Substituting the values into the confidence interval, it is equal to 0.34 plus minus 1.96 into under root 0.34 0.066 divided by 400 gives the lower interval as 0.295 and the upper interval as 0.386. Example 2. Sample size n is equal to 36 and x by n is equal to 0.222. We have to build a 90% confidence interval for the true population proportion P. We use the formula from equation 1, that is Z 0.05 is equal to 1.645. The lower CI is equal to 0.222 minus 1.645 into under root 0.222 into 0.778 all over 36, which is equal to 0.108. The upper confidence interval is equal to 0.222 plus 1.645 under root 0.222 into 0.778 divided by 36, which is equal to 0.336. By solving the following, we get x minus np divided by under root np into 1 minus p, which should be less than or equal to z into alpha by 2, which is equivalent to the following: HP is equal to xn minus p whole squared minus z alpha squared by 2 into p1 minus p all over n, which is less than equal to 0, which is equivalent to the following: HP is equal to xn minus p the whole squared minus z alpha squared by 2 into p1 minus p the whole by n, which is less than equal to 0. HP is a quadratic equation in P. Thus, by solving the solution of the quadratic equation in P, we can calculate those values of P for which the equation is less than 0. Hence, HP is equal to 1 plus Z alpha by 2 the whole squared divided by N the whole into P squared minus 2P bar plus Z alpha by 2 the whole squared divided by N into P plus P bar squared, where P bar is equal to x by n. The solution of the HPR after simplifying: P bar plus Z alpha squared by 2 divided by 2n plus minus Z alpha by 2 under root P bar into 1 minus P bar divided by n plus Z alpha by 2 squared divided by 4n squared the whole over 1 plus Z alpha by 2 squared divided by n. This is known as equation 2. Hence, the upper and lower confidence limits are given by the following. Lower confidence interval is equal to P bar plus Z alpha squared by 2 divided by 2n minus Z alpha by 2 into under root P bar into 1 minus P bar divided by n plus Z alpha by 2 squared divided by 4n squared all over 1 plus Z alpha by 2 squared divided by n. Upper confidence interval is equal to P bar plus Z alpha squared by 2 divided by 2n plus Z alpha by 2 into under root P bar into 1 minus P bar divided by n plus Z alpha by 2 squared divided by 4n squared, the whole over 1 plus Z alpha by 2 squared divided by n, where n is large. Z alpha squared by 2 divided by 2n and Z alpha by 2 squared divided by 4n squared, Z alpha by 2 squared by n are small. Hence, for large sample size n, the confidence intervals given by equation 1 and 2 are approximately equal. Example 1. Let the number of repeated trial n is equal to 48 is the number of successes in the long sum proportion or of the age of success in repeated trial point estimate of p comma p hat is equal to x by n, which is equal to 16 divided by 48. We need to construct a confidence interval for p with confidence interval for P with confidence level of 95%. We use the above discussed formula for confidence interval. 333 plus 1.96 multiplied by 2 plus 1.96 divided by 48 into under root 0.333 into 0.667 plus 1.96 into 2 all over 48 and 4 into 48 into 48, which is equal to 0.217 comma 0.474. Using the simplified formula, interval p plus minus z by alpha 1 2 into under root 0.333 into 0.667 divided by 48 is equal to 0.200 comma and 0.466. Example 2. For a sample size n is equal to 36 and x divided by n equal to 0.222, when a 90% confidence interval is built using equation 1, the CI is 0.108 comma and 0.336. When a 90% CI is built using equation 2, we get the CI as 0.130 comma and 0.353. When the sample size is increased to n is equal to 360, the CI by equation 1 is 0.186 comma 0.258 and the CI by equation 2 is 0.188 and 0.260. Hence, we observe the discrepancy between the CI falling as sample size is increased. Next, we shall discuss about the confidence interval for population variance. Let us take a random sample from a population which has a normal distribution with parameter mu and sigma squared. Then the random variable n minus 1 divided by sigma squared s squared is equal to sigma xi minus x hat into 2 divided by sigma squared has chi-squared distribution with n minus 1 degrees of freedom. Hence, p bracket open chi-squared 1 minus alpha by 2 comma n minus 1 is less than n minus 1 s squared divided by sigma squared, which is less than chi squared sigma squared by 2 n minus 1 bracket close, which is equal to 1 minus alpha. This is derived from the following chi-squared distribution diagram, which shows that the area or probability to the right of chi-squared is equal to 1. Hence, chi-squared implies that for a random variable x having chi-squared distribution with v degrees of freedom is p bracket open x is greater than equal to chi-squared alpha v is equal to alpha. For v greater than 30, probabilities related to chi-squared distribution are approximated by a normal distribution curve. Manipulating the inequalities gives the following 100 into 1 minus x confidence interest for population variance. Sigma is to n minus 1 into s squared divided by chi squared alpha by 2n minus 1, which is less than sigma squared, which is less than n minus 1 into s squared divided by chi squared 1 minus sigma by 2 n minus 1. where S2 is the value of the variance of random sample of size n from a normal population. S squared is equal to 1 over n minus 1 sigma I is equal to 1 to n xi minus x bar the whole squared. For example, we need to construct a 99% confidence interval for sigma squared from a sample of n equal to 16 test runs of petrol consumption of an engine with the sample standard deviation S is equal to 2.2 gallons. Here, sigma squared measures the true variability of petrol consumption of the engine. In order to construct 99%, it is equal to 100 into 1 minus 0.01% confidence interval, that is equal to 0.01. We substitute the data into the CI formula discussed above. Also, we know that chi squared 0.01 divided by 216 minus 1 is equal to chi squared 0.005 into 15 is equal to 32.81, and chi squared 0.99515 is equal to 4.601 from the chi-square distribution table. From chi-square distribution table. Hence, 15 into 2.2 the whole square divided by 32.801 is less than sigma 15 into 2.2 square divided by 4.601, which is equal to 2.21, less than sigma squared, less than 15.78. Example 2. Let us assume that the time in days required for maturation of a seeds of a flowering plant is normally distributed. A random sample of n is equal to 13 seeds gives sample mean x bar is equal to 18.97 days, and 12s square is equal to sigma I is equal to 1 to 13 xi minus x bar the whole square, which is equal to 128.41. We build a 90% confidence interval for sigma squared. From the chi-square table, chi-squared 0.05 comma 12 is equal to 21.03, and chi-squared 0.95 comma 12 is equal to 5.226. Hence, the 90% confidence interval are 128.41 divided by 21.03 and 128.41 divided by 5.226 is equal to 6.11 and 24.57. Let us summarize what we have learnt in this module. An interval estimate is defined by two numbers between which a population parameter is said to lie. For example, x lies between a and b is an interval estimate of the population mean mu. It indicates that the population mean is greater than a but less than b. Confidence interval is used to express the precision and uncertainty associated with particular sampling method. A confidence interval consists of three parts: a confidence level, statistic, margin of error.